In this video, I'm going to explain as simply as possible the difference between scalars and vectors. And to do that, let's start by thinking about what a number is. And this might seem like a stupid question. What is a number? Well, a number, as we commonly know, say the number 3, it tells us the size of something. So we'd say 3 is bigger than 2. And we just all know that based off experience. So it tells us the size of something, and we call this size in physics magnitude. So the size of a number is called the magnitude, and numbers or quantities that have magnitude and only magnitude we call scalars. Those are scalars. So 3 is a scalar, 2 is a scalar, because we only know the scale of the number relative to other numbers, which is essentially size. But what if I told you that numbers can also have another component? Numbers can also have direction. So you could say 3, using that number, north. That doesn't really mean anything because we don't know what the 3 means, but we have a magnitude and a direction. Those two put together gives us a vector. So simply put, vectors are scalars with direction. So a vector is a scalar plus a direction. Now, why is this useful? Why do we have numbers like this? Let's look at some examples in physics. So first we'll look at some scalars, and I'll explain why they're scalars. So one of them, temperature. So why is temperature a scalar? Say you measure 30 degrees Celsius. So we have a scale here. We have a magnitude of 30 degrees Celsius. Now, say you're facing north. Say you're facing south. You measure it facing both directions. This number doesn't change. It doesn't matter what direction you face. It's going to be 30 degrees. And so that's why that's a scalar. How about another one? How about, what's a good example? Distance. If I walk 5 meters east, or if I walk 5 meters west, the distance is still 5 meters. You're not changing the distance. You're not changing the magnitude. You're still walking 5 meters. One more example of a scalar is time. Now time, you might say to me, doesn't that have a direction? And you're right, time does have a direction, but first of all, time only travels in one direction, and it doesn't travel in any spatial direction. So if I measure 2:30 p.m., if it's 2:30 p.m., it's 2:30 p.m. whether I face north or south, whether I jump up or down, it's whether I walk from here to the grocery store, it's still 2:30 p.m., right? So in the spatial dimension, the 3 dimensions of space, it's 2:30 p.m. no matter where I go. And of course, there's time change and stuff, but not considering that, it's 2:30 p.m. Okay, how about vectors? What are some examples of vectors? Now, one is displacement, which is very similar to distance. And I'll show you the difference here, but displacement is the shortest distance between 2 points. So it is a distance, but it's the shortest distance. So to explain the difference between the scalar distance and vector displacement, let's say someone walked along a path like this, something like that. So they start here and they end here. The distance they traveled would be if you stretched this curved line out into a straight line and took a ruler and measured it. That would be the distance. The displacement would be this line here connecting the start to the end. So it's the shortest distance between the start and the end point. And that obviously has a direction because depending on how they traveled, there's a direction to the start where they start and then where they end. The distance has no direction because you could walk in any sort of path and end up at the same endpoint, and the displacement would be the same. In other words, we only care about the magnitude of this distance, whereas here we care about the magnitude and the direction. Another example of a vector, maybe an easier example to think of, is force. So force, and I'm not getting into the math of anything here, but force, if you push something, say you have I'm going to draw a coffee cup here. You have a coffee cup like this. If I pick it up, I'm pushing upwards. So I'm exerting a force upward on the cup. And so that force has a direction because I'm pushing the cup upwards and thus exerting a force on it. If I put the cup down on the table, you have the force of gravity pushing down on it, and then the force of the table pushing back on it to keep it still. So force has to be applied in some direction, otherwise there's no force applied on it. So that's why force is a vector. Now, all quantities in physics, at least early on, are scalars or vectors. If you want to look way down the line into more advanced stuff, there are things called tensors, which are very advanced and complicated. But for now, everything is a scalar or a vector. And because of their differences, vectors have to be treated much differently than scalars. They have different rules for how they add and subtract and those things. And so in the following videos, I'm going to go through everything you need to know about vectors and how to use them. Thank you for watching.